Hello and welcome back to Introduction to Cognitive Science. Today we are going to continue our journey towards exploring how our growing understanding in the field, as it's developing, of the brain, the actual brain, not just what we believe minds can and should be, but what the brain is actually doing, how these things start to inform not just our understanding from the imaging side and all that stuff that we talked about last time, and the physical features, but kind of percolating up to what do some of these raw findings in neuroscience say about the way that the machinery of the brain works. So we'll start talking about connectionism. So, modeling brains. So far, we've talked about measuring the brain. We've seen evidence of ways that the information travels, right? So from the landmark studies with the monkeys trying to get their food fix, there were two different visual pathways, right? We had the dorsal pathway, which, again, the dorsal fin on the back, goes up to the parietal lobe to help you process visual information spatially, and then the ventral pathway goes towards the temporal lobe to help you process it more in a languagey way, more of a symbolic naming it sort of way, the auditory way. So, part of this, though, we've got these interesting findings, and we're beginning to be able to document some of what we see, but part of science, and this is going to be a little aside, part of all of science is creating predictive models. We need models that can predict how this stuff works, not just sit here and cut it apart and understand, ooh, this is interesting, I am at least documenting what's happening. But in science, we need to be able to create a model that helps us predict what is happening. And we need some way to characterize the functionality. How are the neural populations of the brain actually working? And, you know, it comes down to this feeling of like, oh, well, if I can just observe the brain, then I can tell a lot about it. And that's true. But getting a more mechanical understanding, a more how do all the parts move around understanding is pretty key to this being science and not just an interesting expedition to document things. So, let's talk about models. A little aside into modeling and models in general. So, what is a model? This is something that you might not have thought before, or you might be very familiar with, but it's something that comes up all the time in science, but it's sometimes not well defined. In fact, it took me till partway through grad school to realize there was this unifying concept of what model means, and I'm going to try to give that to you here. So, a model is anything that is a reduced representation of something real, a natural phenomenon. It's specifically designed to highlight relationships in the data, in the world, the way things relate to one another, not just be a perfect copy, right? And it helps us to make predictions. So, and this is important, this is a quote from George Box, all models are wrong, some are useful. So, what does he mean by that? If a model was not reduced, and in a reduced form, it would just be the world, right? And so this spectrum I've put up here, the more reduced form a model becomes, the kind of more abstract it is. It's not really capturing, it captures less and less of the actual world, but it's still designed to highlight something useful, right? So, and then the further to the right, more concrete the model becomes. So actually just being the thing in the world. A very robust model, but maybe a little less useful for certain predictions. So let's do a little exercise. Is this a model? Yeah. Yes. What is it modeling? Well, it's got a pretty good representation of the shape of New York State, but what's missing? What is it reduced? Where are the trees? Where are the rivers? Where are the birds? Where are we? Where are the people? Where are the highways? Right? This is a model. A map is just a model of the world. But it does help us make certain predictions, right? Like, if I'm in Oswego County and I move south, I'll end up in Onondaga. That is a prediction that we can make using this model. So, let's talk about analytical versus other kinds of models. We'll start with analytical. Analytical models are these closed form, static math type models, right? We typically derive them using statistics and real world observations. We kind of come up with these formulas that help us make sense of the world, right? And they're pretty good at predicting outcomes. They're not so useful for thinking about the intervening steps. It's more about, hey, if I give you the initial conditions, you tell me what's going to happen at the end. So one of the simplest models that we know of is, in physics, gravity. So on Earth, the equation for gravity is, you've probably seen this before, things fall at 9.8 meters per second per second. So the position of anything that is falling, and based on the time it has been falling, is going to be negative 9.8 meters, so less than it was. But each second that's going to get bigger, right? So this is going to grow and grow and grow, and you're going to fall faster and faster and faster, right? Basics, simple stuff of physics, right? So the thing about this is that this is a closed form analytical model of how gravity works on Earth. So we can actually accurately predict how high a ball is at any time after it starts to fall. Let's look. Here's a ball at 100 meters, right? We let it go, it falls 9.8 meters. And then thereafter, it's going to fall faster and faster until it hits the ground and then stays there, right? But what the idea is here is that we can take this equation, plug in any value for the seconds, like how long has it been in the air, and I can tell you how far down it will have fallen. Whereas moon gravity, for example, is 1.62 meters per second falling, so negative. Same idea, but now I have a different set of patterns. The ball falls less, but it's still increasing in speed. Until it finally hits the ground, right? It takes longer. This is the idea of a predictive analytical model. And we use these a lot in science. Here's another predictive analytical model. So here is a very basic model of the world. You might not think of it like this, but any given person, I can model their weight just by knowing the average of all the weights of all the people in the world. That doesn't sound like a model, right? It's just a single value. Everyone in the world weighs 150 pounds. That's a really dumb model. But it's still kind of useful, right? Say if you have to design an elevator and its occupancy is maximum of 10 people, probably. Well, your elevator better be able to hold at least 1,500 pounds, probably 2 or 3 times that, just to be safe, right? So even just a very simple single data point, or perhaps not data, but a single value, a mean value, can be a model of the world. It's just a bad one, right? It's still a useful one in some cases, but it's not very robust. So we can add extra parameters here, add things that help us make a better prediction. So for instance, we can add height to our model. One additional parameter, so mean weight's not going to change, but the individual person's height might. So mean weight plus or minus some amount for each inch of height added to from their body, right? Or we can have multiple parameters. So we can say mean weight plus something about their height, but also times their daily caloric intake. You see how this is getting more and more complex, right? We are able to capture a more accurate version as the model gets more complex. There are lots of these in psychology. For example, the time it takes you to forget a memorized fact or a set of memorized items, although usually sort of arbitrary ones in a laboratory setting, that's a well-known model. There's also the power law of practice. So the longer you practice, the more you will improve, but there are diminishing returns. These kinds of models are super useful. So we're going to talk about a different kind that is pretty important, but the idea here is that these are sort of reduced, very, very sort of logical and very clean models. There are also less clean models. What is this modeling? I'm sure you know. It's a hurricane. Can I capture a hurricane? A model of a hurricane? Using one formula? Absolutely not. You have to do a whole different approach to capture something as complex and dynamic and messy as a hurricane. What about plate tectonics? These are also simulations. They are trying to imagine what each and every step, each and every particle is doing to result in the Himalayas. Because we couldn't be there, obviously, we don't know. But we can predict, we can make models that help us simulate what could happen. These are computational models. So I think this just bears iteration because these come into play quite a lot with the brain. And the philosophy of these ones is, I don't know the end. I don't know what the end result is going to be when I launch this simulation, this computational model run. But I can guess what comes next at each step, right? So when you're modeling very complex systems that you can use this step-by-step simulation to try to actually produce the behavior, right? The hurricane model is a prediction of, based on what we know about the way particles in the air interact and currents and heat and moisture, where the things are going to move. So these produce actual behavior, right? It's not just the numerical outcome that describes some end result, but it is the behavior step to step. And so these things take a lot of computational resources. In general, these are both useful approaches. And there's some overlap too, right? So I might include the forgetting formula in my computational model of, like, solving math in my head. There's a whole architecture, Act R, that does that kind of stuff. But in general, these are two sort of different takes on the ways that we can talk about producing good predictions, right? So analytical models try to predict individual outcomes or specific outcomes, and they're easy to compute, and we can get them out of data analysis pretty well. Computational models are sort of a different path. They let us simulate behavior sort of in a forward-facing way as opposed to a backward-facing way, and say, I'm going to try to go at each step and see how the behavior plays out, and then we, the researchers or whoever is interested, can say, okay, that was close to real, or it deviated in this specific way, or whatever. So yeah, we have to compute each step, and we can ask, how does the behavior actually play out? So Sherdlu is a computational model of language. Just think about that a sec. So it doesn't have an ultimate destination. It's just you give it things and it tries to solve them forward, right? So here comes the question of where we're heading with this. How plausible is a Sherdlu? Not specifically Sherdlu, because everyone knows it was just written for a demonstration in a micro world, right? But how plausible is the ability for Sherdlu to simulate this sort of behavior? How do we get that down into brainland? Well, we are now tapping into neurally inspired computational models. So, if you think about neuroscience, we are examining very basic brain activity, so the stimulation and transmission of neural signals from one neuron to another, but also at the whole brain level, we see sort of a overall picture of where activity occurs, right? So, how is the neuron built? What does it do? And then at the very top, with the neural imaging stuff, what are the overall functions that change, right? And so we have these two sort of disconnected things. We have the very, very small individual level measurements of how the mechanisms of the neuron work. And then the overall, we know sometimes certain kinds of brain regions getting damaged changes the function of the brain. Connectionist models come in the middle to give a stronger take on the algorithmic level of analysis for all of neural activity. So, here we are in connectionism. Connectionist networks. What are connectionist networks? You might have heard of them already as neural networks, right? There's a lot of machine learning stuff going on in the modern world, and there's a lot of this sort of mass distributed processing stuff happening. Well, we're going to dig into what is that at its base level. So, at the highest level, at the sort of computational discussion of this, it's a way of processing information that uses a large number of very small processing units. And when those units come together, they can combine the signal across all their units in unique and interesting ways that, again, are themselves simple at each step, but they allow us to do a huge variety of functions, which we'll cover further later. So, what's the flow like in a connectionist network? So, every unit in one of these networks is called a node. Each node can be linked up to other nodes. Those links will have weights that help the next node in line understand whether or not it should turn on or not, right? And so one of those links can either stimulate, so if this node is lit up, I will spark the next node, or the link can be negative, it can be inhibitory, so if this node is lit up, I'll prevent the next node from lighting up. We won't, I'm going to walk through a quick one. So here's a little network, right? Nodes on the left will flow towards the nodes on the right. Say one of these is lit up and one of them is dark. And depending on how the links are set up, the connections between these nodes, you could have the fact that the bottom one is lit up can be impeded by the fact that the other one is dark in such a way that, say, now the middle layer, only one of these nodes lit up, and then on the output end, another one, the pattern is reversed. We've just knotted the start. We'll talk more about how weights work and everything later, but this is just to give you an idea of how this information kind of percolates through the system. So some set of nodes all feed into another set with little tiny combinations that will cause it to either light up or not, and then it'll go on to another set, right? And so on through the entire brain. So, what are some of the features here? This is so if you take anything away from understanding connectionist networks here, some of their features are represented here. So they always involve parallel processing. So you're not waiting for one node in one layer to finish so that the next one can figure out what it needs to do. They are all doing their thing together. And also, the information is not packaged neatly into a single node or a single overall larger symbol. It's very loose. A single node might only be able to capture a single bit or a single small pattern of activations. And the rules are simple. There's no complex grammars, no machine tables, no looking up a bunch of different complicated states. It's just nodes talking to their neighbors. So, but the idea being that from these simple rules, more complex behaviors emerge because they're all jammed in there together and connecting. So let's go over some more of the sort of the fallout of this, right? Because I've already described to you primarily the basics, but what does this imply about the way these networks can work, right? As discussed, these are simple rules, but what's interesting about these simple rules? So here's a few concepts we'll touch on. Parallel processing, as just discussed. The idea of graceful degradation, that these things don't die just because some part of them isn't working perfectly, right? And then learning. These networks can actually kind of learn on their own almost just naturally. So let's talk about it. Serial processing. So standard information processing models up until now have all had this serial bottleneck. They've all had the idea that information is going to move one symbol at a time, right? Think of the Turing machine. It takes a symbol off the tape, and it consults the machine table and its internal state, and then it changes it or moves. It might be able to process a whole bunch of this stuff, but it's still one at a time. It's all serial. It has to happen one at a time. But let's look at something as complex as image processing. Do you think our neurons or anything is going to move fast enough to process all visual information in an image serially? Well, let's talk about parallel processing. Remember, a lot of units can be active all at once. We don't have to just go one step at a time waiting. We can perform a lot of these, what you might think of as steps, simultaneously, and pass them along to the next layer and just go. So the input can come in an array, as opposed, I say an array, sorry, it's a sort of a comp sci term, as a group, as a set of information, not just a single piece of information, and it can all get processed together in step as it moves from one population of nodes to another one. So let's have a little exercise to show how this might work. Quick as you can, what is this image? You probably got it pretty quick. That's a cat. Meow. It's my cat, a little bit. She's great. She likes to sleep like a shrimp. You processed that pretty dang quickly, right? You figured out, because it actually wasn't perfectly clear right away, because it's sort of a circle. Then you notice the legs. Oh, and then it's, okay, the ears there. Okay, great. This is a cat. Great. How'd you do that so quickly? Well, there's a couple of theories on the table here, right? And we're not going to get into all of image recognition, but I can tell you in broad strokes, you notice certain features of this image that let you know that this was a cat. It was a mammal at least. It has toesies, and it has ears, and it's a cat. So how did we do that? So let's look at a little strip of this image, boop, and we're going to convert that into a set of colors, right? So our eyes are capable of taking in colors, and then we can start operating on those colors, right? In the serial world, in Turing style, we would have to go one pixel, one little chunk of visual information at a time, back and forth, move along, la-di-da. In the serial processing world, we could have one node ready to receive each of those pixels all at once. Another set of nodes that are all bound up to those ones to convert those into something else that's meaningful. Like, oh, there's a thing here and a thing here. The rest of them are kind of light. And so on, up through the feature detections of eels detection and toesies detection, right? All at once. Moving one flowing step at a time. It's still serial in the sense of course, it has to move through the system, right? But it's moving in a mass distributed way, as opposed to one single focus point at a time. This is the difference between a serial approach and a parallel approach. So, serial versus parallel. This is an extreme example, but let's do a little math to throw it out there further. Let's say it takes a neuron 5 milliseconds to fire, 0.005 seconds. And let's say we have one 400 by 500 pixel image of a cat. That's 200,000 pixels. It would take one neuron moving serially 16 minutes to process that image. You did not take 16 minutes to process that image. Now, it's extreme, because we wouldn't expect a single neuron to be responsible for processing all of vision. But kind of the point is that, well, if it's not a single neuron, then it's not a single processor, so it's parallel. But, again, it is still moving forward, right? It's not like we have all neurons in the brain all light up at once. So there is some amount of serial going on when in the way that we process the world, but it's by and large very distributed. So another topic, another interesting property of these things is graceful degradation. You don't, if the networks are set up such that the neurons will respond if there's a signal or not, right? And they have different weights that will change the way that all works. Well, you don't need perfect information anymore. Symbol systems either will work or have some critical error, right? Oh, this was a symbol that was outside of my alphabet. I don't understand it. The Turing machine cannot work anymore, right? Unless you have a lot of redundancies to kind of fix that and say, oh, well, these are the symbols that exist, but these ones only these are allowed, whatever. The information flow in a connectionist network doesn't care. It doesn't matter if some data is missing. It might not light up the way we would want it to if the data is missing, but it still works. Every node can still do its job, even if some of them are dark when they should be lit up. And it can be quite robust, right? So there can be missing data and still we can get pretty good answers sometimes, which is part of why the system is able to compensate for damaged or missing parts, as we discussed last time. Real quick, what is this image? Probably a lady, right? Or someone at least presents femme. This is nothing. There's no information here, except for the very broadest strokes of the edge. But your brain is saying, hey, I kind of recognize that. The outer edge networks are saying, hey, I think there's somebody, female here, female-ish presenting here. And the rest is like, well, I don't know. I don't see any face. I don't see any color. I just see an edge. So sure, we'll guess that this is probably someone femme. Okay, that's exactly what I'm talking about. This is the ability for your system to take an incomplete, kind of garbage piece of data and make sense of it very quickly. You still had some idea. You're not certain. There's a lot of information missing, but the impression was there. There's also the capacity for these systems to learn. So the weights between the nodes in the system can change. They can change dynamically. There's this concept called backpropagation, which we'll cover in the future, where if the system's output doesn't quite match the reality that it expected, you can send an error signal back and say, hey, change these weights. You can train these networks. You say, hey, try to recognize this number, this written number, and then when it says, oh, that's a 3, and then you say, no, it was a 4, it will change all of its nodes to change it, right? To keep exploring the space. I know it's a kind of abstract thing right now. We'll go into depth in the future. Just know that these weights can update, right? So it's not fixed. You can change them. You can train them. And then in the future, they can, do their pattern matchy thing. Example of this, you may have heard of Deep Dream, Google's AI system that seems to just turn everything into dogs. The idea here is that Deep Dream is doing its best. It's a prediction. It's a system that is doing its best to predict what is in each image. Now, the reason we get all these ones that turn everything into dogs is that this is sort of an interim step that makes things kind of trippy and weird, that stops it. But the goal of these systems is not to turn things into dogs, but it's to predict what is this image, what's actually in it. And so the step here would say, no, that's these colors and shapes don't match the reality, and it would update and try again. The dogs is just sort of the middle step of it thinking everything is dogs. So that covers some of the basic interesting stuff about connectionist networks. They're this new way of thinking about how we run data around inside of a system, and they're in the realm of plausibility for neurons. Neurons seem to have these node properties. They have more. They're complex little biological entities unto themselves, but we can talk about them at this level, sort of bridging the gap up to how does this make cognition happen. So again, parallel processing is this idea that they are processing a whole bunch of stuff all at once in step together. And it makes them very fast, right? They can process a lot of information together. Although it can't do a lot at each step, so it still has to propagate forward. Graceful degradation is that you can have an incomplete, damaged, or imperfect signal fed into the system, and most of the system can still just be intact and continue on. It doesn't error out. It just goes, And they can learn through exposure. So a node's weight can update either just by the nature of it firing more often, or it can receive feedback signals and change itself. These are all great. These are all great properties that kind of align better with our understanding of human cognition, right? So let's do a walkthrough of how we might look at applying a connectionist network approach to something that we've already talked about, edge detection. So we can look at these basic ideas and how they can contribute to a model that, kind of like Marr laid out for early vision, of turning a raw light pattern into some internal sense of where the edges are within that light pattern. So let's do this. Consider this truck. Just a simple keynote auto shape. It's a truck, right? It has a background and a foreground, right? We see the truck's image is this darker blue, and the background is this sort of faded nothing blue. It just feels like background. How would you process this? You can tell right now there are edges all over this. You know this. You can use those edges for many, many things to make this simulation. I mean, this is sort of cartoony, the truck, but you can pick up this more abstract concept of the truck. So to begin that process, you need to detect all these edges. How could a connectionist approach do this? It'll be similar to what we showed with my cat before, but let's zoom in on a chunk. So let's look at this back, because it's simple and straightforward to look at a single vertical edge. So this is the light pattern, right? This is the light that's coming into your eyes. There is a bright, I'll call it bright, I know it's darker, but like sort of a more colorful area and a less colorful area. We could represent this in a connectionist way with, say, for example, 6 by 6 nodes, 36 nodes. So, okay, what have I just done? What I've said is I've got 36 nodes, and they're all, each one of them is pointed at a different little region on this screen, on this light pattern, right? Each node will have a value based on the light that's present there. So the more colorful light is at the value of 30, the less colorful light, we're just throwing it at 0, right? It's at a low number. So I have 36 nodes doing this, representing the light pattern, the amount of color, the amount of light color hitting the eyes. I can also have an edge detector, a set of positive and negative weights, values, that will combine to determine whether or not the little region that I'm looking at right now is an edge or not. Now, this one is weighted with positive values on the left and negative values on the right. The idea just being, we'll sum all these up, and we're going to run this over the full array of the other nodes and get it all, right? So the result would be this edge pattern. The idea is this is going to be the resulting internal representation of, hey, I'm running my edge detector over this light pattern. I want to know where do the edges live, right? So let's do it. We have our pattern here. For each one of these, we're going to do the same kind of calculation. We're going to look at it all at once. Just be prepared. So for this little region, all these 30s, right? We're looking at a region that, what would you think? Just at high level before we do the math. Is this an edge? This little area I'm looking at, is this an edge? No, they're all the same. There's no differences here. So this edge detector pattern, this sort of the weightings that we have here for the connections between all of these light patterns and the edge pattern, is we're going to multiply each node and then sum them up. So 30 times 1 plus 30 times 0, so neutralize the middle, and then 30 times negative 1. Okay, so that's going to be 30 plus 0 minus 30. Okay, so that's going to be 0, and it's going to be 0 everywhere, right? So when we do the math on that whole region, for just that one region, we get a 0. What about the next region? Well, you'll notice the math has changed. There's no longer, the negative weights are no longer getting a signal at all, but the positive weights still are. So this is an edge. There's a differential here, and this little edge detector set of weights can detect it. This sums it up to a 30. The next one still sums up to a 30 because there's still nothing in the negative zone, but there's still something in the positive zone, and then a 0. On and on, all the way down the line, until we have an internal representation based on the light pattern that tells us, hey, where is the edge? This is great. This is the zoomed in version. Now, I want to make a note here before we wrap up this example. It's important to recognize that I have arranged these things in this pretty little light pattern shape for our sake, right? The nodes, they don't care. They don't care where they are. The first node in like a long line of nodes could be looking at the bottom right corner of the light pattern. The second node could be looking at the top middle. It doesn't matter to the nodes. So a more sort of honest way of arranging this in a connectionist fashion would be something like this. So if we were looking still at that third edge detection moment, the way this would actually look would be one big old 36er array of nodes, and then the weights between them are the edge detectors. So I've kind of changed the colors a little bit. Looking at this top one, it's just top left, and then we sort of carriage return, right? So top left is blue, 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 kind of light, light, light. And then we go down a row, blue, 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 light, 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 etc. They could be even more randomly scattered. It doesn't matter. The nodes don't care. But all that matters is how they're connected. And so these connectors are what define the spatial relationship. It's a little abstract, but you can see how the weightings between these things. So the dots would be a neutralizing one. The solid small pink line would be the positive weights. And I made the red one a little thicker to be more noticeable. Those would be the negative weights. until we get a positive value here. We sum all of those up to activate that next connectionist node. Okay, so that's just to remove the metaphor, but the idea still holds. This is a little set of tiny math that you do a whole bunch of at once, and you are able to process the world into a different form. So let's look at our truck again. We could probably expand this a bit. Let's look at just do it over a larger set. You could have a huge number of parallel things, right? Do it over the whole image. What do we get? If we do this same process, if we have a set of some sort of network that maps the raw light pattern with all these negative and positive weights summing things up to a different shape, internally we get the edges. We know the edges, we know where they are, we can see them directly. And that's edge detection. So, this is, I think, a good example of how you can take a large set of small operations to create new useful representations of something visual, right? It's mass distributed, so they don't depend on one another, right? They depend in one order, so from the image to the translated version with the edges, but you can do them all at once, all together. One big neural population can do this in a single step. So that's connectionism, or at least the general edges of it. There's more to the picture, of course, but let's get so it's difficult to model certain cognitive abilities exclusively using the rules and symbols of the world. Image processing is a perfect example, and connectionist networks are the algorithmic take on how we can connect brain functions and neural activity. So, I want to leave you with a very interesting take on this whole approach. Spawn. It's a massive neural simulation composed entirely of little simulated bundled up neurons, just the neurons themselves, but bundled up in this similar way. And this is a model that's capable of recognizing digits and letters, right? So it processes all the edges and turns it into some internal value, and it's able to consult internal instructions that it knows and then write out answers. Not literally physically write them out, but still give enough detail that it could do such a thing. This uses the semantic pointer architecture. Interesting thing, you can look into that if you're curious. You can look up the Ningo program, and this is out of the University of Waterloo. So, short video describing Spawn.
My colleagues and I at the University of Waterloo have built a large-scale model of a functioning brain called Spawn. The model receives its only input as a 28 by 28 pixel image and controls a simulated arm. In this video, we see both the activity of the various brain areas and decodings of the neural representations in those areas. The first task is a recognition task. Spawn writes the digit it sees in the image. Individual neuron voltage spikes are shown scrolling through the thought bubble at the back of the brain. The decoded value is displayed on top of that activity. The second task is called copy drawing. Instead of just recognizing the digit, the model must reproduce the style of the digit. Here it successfully copies two styles of the number 2. Spawn's representations are thus useful for both categorization and encoding fine perceptual details. The next task is a counting task. This task demonstrates that Spawn can not only represent and categorize numbers, it also has an understanding of numerical concepts like order. Spawn is first shown a number to start counting from, 4, and then it is shown how much to count by, 3. We can see the internal progression of numbers as it counts and finally writes its answer. Next, we have a question answering task. Here, Spawn memorizes a list of numbers and then answers a question about the list. You can watch the topmost working memory as it stores the items in the order they are shown. In this case, Spawn is asked what is in position 5. Spawn answers the question by decoding its working memory and using the result to drive the arm. The final task is a serial working memory task, in which Spawn must memorize a list of items in order and then repeat it back. We have seen several tasks that Spawn performs correctly, but the errors it makes are equally important to determining if it is a good model of human cognition. Note that the darkness of the letter in the thought bubble indicates how well that item can be decoded from the current representation. Spawn is now drawing its memory of the list. But when it gets to the 8, it is no longer confident in its own decoding of that memory, so it draws a horizontal line indicating it has no answer. If we look at the pattern of errors over many versions of Spawn, we will notice that it matches the details of human error patterns. We have now seen half of the tasks that Spawn can perform. The rest are in other videos on the nengo.ca website.
So, consider that. All right. Final thought. Think about other things you process in your day-to-day life. Ways you realize, imagine, notice, or react to things. Think about how quickly you achieve them. Do you think they're more serial or distributed? All right. Thanks. Take care.